Hello, welcome back. In section 2.6, we study moments and center of mass. So in this particular video, we are going to be looking at the center of mass and moments in a one-dimensional context. So let's take a look at our teeter-totter here. At least that's what I call it. For those of you that are old enough to know what a teeter-totter is. A teeter-totter in a playground was a big board, and it had some kind of a fulcrum in the middle, and one person would sit on one side and another person would sit on the other side, and you would push up and down, and you would go back and forth, you would go up and down and up and down. That's called a teeter-totter. That's basically what we're going to be looking at today. Good thing I wasn't ever tried to be an artist. So this is the fulcrum. It is the balancing point. And what we want to do is we want to balance our masses. So we have a mass over here, mass 1, and we have a mass over here, mass 2. And if we want to balance the system, we have to adjust the distances such that mass 1 times distance 1 is equal to mass 2 times distance 2. So as an example, let's just say that mass 1 is equal to 10 and distance 1 is equal to 2, and mass 2 is equal to 20. What would distance 2 have to be? Well, mass 1 times distance 1 is 20. And so if we call that x, then we have 20x. And so dividing both sides by 20, if we set them equal to each other, we get x is equal to 1. All right, so basically we just created a little equation, m1 times d1 equals m2 times d2, and solved it for distance 2. All right, now, in most cases, what we want to do is we want to keep the fulcrum, we want to keep the masses, as it says, the masses are not allowed to move, and instead we balance the system by moving the fulcrum. So in this particular case, x bar is our fulcrum, and we want to move the fulcrum so that the system is actually going to balance. And so to do that, we can do this little algebraic thing here. And that's pretty simple to understand. Over here on the left-hand side, we basically have m1 times d1, right? Where distance 1 is the difference between x1 and x bar. So we're just taking the difference between these two. And it's the absolute value, so we want a positive number. So it's not going to make any difference whether it's to the left of the fulcrum or to the right of the fulcrum. And then we do the same thing over here. We have our mass times the distance. So we're using the same formula, m1 d1 equals mass 2 times distance 2. It's just the distances are being measured as the difference between the fulcrum position and the mass. And so using the distributive property to multiply through, doing a little bit more algebra, we come up with this relationship right here, which, in case you can't see that very well, it's x bar, the fulcrum, is equal to m1 times x1 plus m2 times x2, and that's all divided by m1 plus m2. Now the numerator of this is called the center of, it's called the moment of the system. It's called the moment of the system. The moment is the mass times the distance, the sum of the mass times the distances. So the numerator is the moment, the bottom is the total mass. So you have the moment over the mass. Okay. So in general, if we have numerous points, I mean, we could have more than two masses. We could have three masses or four masses or five masses. We could have an infinite number of masses theoretically, and we want them to balance. So the general formula is we take the sum of the moments and we divide it by the sum of the masses. All right. And here is our general statement on that in the box. So right here, it tells us sum of the masses. Here we have the sum of the moments, capital M. And so then the center of mass, x bar, is capital M divided by little m. All right, so let's do an example. So we have 4 point masses placed along a number line. Right? See, thinking about it as a number line is the easiest way to think about these problems. So we want to find the moment first. Okay, so the moment are the sum of the masses times the distances. So moment 1 is 30, and x sub 1 is negative 2. That's its distance. So I multiplied them there. Mass 2 is 5. Its distance is 3. I multiplied them there. Mass 3 is 10, and it's 6. Multiplied them there. And 15 and negative 3, got those guys there. Multiplying them together and then adding them up, we get the total moment is negative 30. Now, we want to find the total mass, all right? And so the total mass is just the sum of the masses, all right? So we're simply going to add up the masses, 30 plus the 5 plus the 10 plus the 15. So I've got that down here. And that becomes 60. So then the fulcrum, x bar, is capital M, center of the moments divided by the center of mass, which is negative 30 divided by 60, or negative 1/2. So that means that the fulcrum, if you were thinking of this as an x-axis, would be at the point negative 0.5. Right? So here's 0. So the fulcrum is going to be just to the left of x equals 0 to balance these 4 masses. Alrighty. Now, let's generalize this. We've been talking about masses along the x-axis in one dimension. But now we want to look at masses in a plane, right? And so the idea is essentially the same. We need to calculate total moments, and we need to calculate the total mass. Now, what's going to be a little bit different is calculating the total moments. Now, once again, if you want to complete a development of this idea, go to the textbook, and they spend considerable time developing these formulas right here. But I'm just going to cut to the chase and get to these formulas. The only thing that I want to say about the formulas for moment, and so this is the moment about the x-axis. M sub x is the moment about the x-axis. M sub y is the moments about the y-axis. So let's just take a look at what that means. So here we have our y-axis. And so if we want to find the moment, so we have a mass right here, M1, and the moment of that particular mass is the mass, okay, so the moment, M sub y, is going to be mass 1 times its distance from the y-axis. Well, now the distance from the y-axis is an x value, so that would be x sub 1. right? So here's the tricky part. When you're finding the moments about the y-axis, you are actually using the x values to calculate that. Likewise, if you're calculating a moment about the x-axis, okay, this distance here is going to be a y value. So you're going to take the mass, and you're going to multiply it by a y value. And so that's why in this formula down here, the total mass about the x-axis, that's what m sub x means, is the sum of the masses times the y values of the ordered pair. Because we're talking about a plane, so we have an ordered pair, an x1, y1. And the total moment about the y-axis, we sum up the masses times the x values. Calculating the total mass is exactly the same as what we did. We add up all the masses. And then the formula for the coordinates of the center of mass are essentially similar. X bar represents the x coordinate of the center of mass. Y bar represents the y coordinate of the center of mass. And so take note that when we're finding the x coordinate, we are taking m sub y. And when we are finding the y coordinate, we're doing m sub x. All right. So again, you've got to keep that kind of straight. So let's do an example, and it will all make perfect sense. So suppose 3-point masses are placed in the xy plane. All right. So essentially, here's what we have. If I can draw just a little picture over here. We have at the point -1, 3, -1, 1, 2, 3, we have a mass. And then at 1, 1, we have another mass. And then at M3, we have 2, -2, 2, -2, we have another mass here. And so we want to find the balancing point of these. The x and the y coordinate, where all three of these would be balanced in the x direction and in the y direction. And so first we're going to find the moment about the x-axis. Okay, so in other words, we want it to balance around the x-axis. Okay, so we want to balance it around the x-axis. So just thinking of it temporarily in one dimension, how would we do that? So we want to take the sums of the masses times the y values, right? And again, why the y values? If we're balancing it around the x-axis, then we need to know all of these distances, right? And those are y values. Those are going to give us y values. So we take the mass, which is 2, times the y value, 3, 2, and 3. 6 times 1, which is the mass times the y value. 4 times -2, which is mass 3 times its y value. And we get 4. Then, to find the moment about the y-axis, now we want to balance it in this direction. So we need to find these distances. And those distances are x values. So we sum up the masses times the x coordinates. So again, 2 times -1, 2 times -1 is the x value. 6 times 1, 1 is the x value. 4 times 2, 2 is the x value. And we get 12. So that's the moment about the x-axis, the moment about the y-axis. The sum of the masses is 12. And then to find the x-coordinate of the center of mass, we simply take m sub y. Again, remember that's backwards. m sub y, because remember, m sub y right here, we're working with the x-coordinates, right? So if we want to find the center of mass, the x-coordinate of the center of mass, we have to use the calculations where we're using the x-coordinates. That was m sub y. And so we end up with 1. Likewise, we want to find the y-coordinate of the center of mass. We have to go to the calculation where we were using the y-coordinates, which was m sub x. Divided by m, we end up with 1/3. So I didn't write it as an ordered pair, but technically speaking, the answer to this as an ordered pair would be the x value is 1 and the y value is 1/3. So 1 and 1/3, so if we go 1 and 1/3, that means something like right about in there. Right about there. At x equals 1 and y equals 1/3. That point right there would balance in the x and the y direction. So in other words, if this was on like a big piece of paper or something, and you were to put your finger underneath there, it would balance perfectly on your finger, that being the fulcrum, if that makes any sense. Okay, next video, we're going to take a look at the center of mass of thin plates.